So in case of aldehyde, sigma bonds are with carbon atom, hydrogen atom and oxygen atom. And in case of ketone, it is with both carbon atoms and one oxygen atom. CH2O. What is CH2O? It is HCHO. What is HCHO? It is methanol. So you're getting a mixture of two different aldehydes, that is ethanol as well as methanol. This much part will remain the same. Nothing will happen to the double bond also. CN will change to CHO. Aldehyde you are going to get. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 2 of the chapter Aldehydes, Ketones and Carboxylic Acid. So in the last session, we started with what are aldehydes and ketones, right? We had an introduction to that and then we discussed the nomenclature of aldehydes and ketones, that is IUPAC as well as the common names of aldehydes and ketones. So in today's session, we are going to first see what is the nature of carbonyl compound and then we are going to study the preparation of aldehydes and ketones. In details, we are going to study the preparation of aldehydes in this session. So to begin with, the nature of carbonyl compound. So the carbonyl carbon in aldehydes and ketones is sp2 hybridized and forms 3 sigma bonds separated by 120 degree from each other. So what was the structure? As you can see, this will be your aldehyde, right? And the general structure of ketone is RCOR dash. Okay, so in both of these cases, the carbon atom is sp2 hybridized. Now, why it is sp2 hybridized? This carbon atom, which is the carbonyl carbon, is further attached to 1, 2, 3 other atoms. So it is sp2. That is 1s and 2p will give you sp3. So like this, you can remember. So here also, it is further attached to 3 other atoms. So this is also sp2 hybridized. So this carbon atom is forming 3 sigma bonds, right? One sigma bond with one of the other carbon atom, which is part of the alkyl or aryl group. Another one with the hydrogen atom, or in case of ketone, another alkyl group or aryl group itself, and one sigma bond with the oxygen atom, right? So totally 3 sigma bonds it is forming. Now you have a double bond here also. Now how double bond is formed? It is formed by the pi bond formation, right? So let us see. So one of the sigma bond is formed with the oxygen atom and the other two with the carbon and hydrogen atom. So in case of aldehyde, sigma bonds are with carbon atom, hydrogen atom and oxygen atom. And in case of ketone, it is with both carbon atoms and one oxygen atom. So in both cases, you can say that totally 3 sigma bonds will be present. Now, the 4th valence electron, which remains in the unhybridized p orbital, overlaps with the p orbital of the oxygen atom to form pi bond. Okay, so this, how is sigma bond formed, how was pi bond formed in detail, we have studied in class 11 itself. So only 3 orbitals of the carbon atoms are taking part in hybridization and forms 3 sp2 hybridized. So let us see the electronic configuration of carbon. It is 1s2, 2s2, 2p2. Atomic number of carbon is 6, right? So this is the 2s which I have drawn here. This is the 2p. So in 2s you have 2 electrons and in 2p you have 2 electrons. So as discussed now, it is going to be sp2 hybridized carbon. The carbon is sp2 hybridized. So this electron shifts here and carbon in its excited state will have s and p3. This will be the structure, right? Electronic configuration. Now this s orbital and 2p orbitals will undergo hybridization and form 3 sigma bonds, right? Now what about this last orbital which is not taking part in hybridization? The orbital which does not take part in hybridization, that will form the pi bond, right? So the oxygen atom has 2 lone pairs of electrons which occupy its remaining 2 orbitals. The carbonyl carbon and the 3 atoms bonded to it lie in one plane and the pi electron cloud is above and below this plane. So let us discuss the structure and the nature of the carbonyl compound, right? So as you can see here, this is a ketone which is represented here. You have the carbon and on either side you are having alkyl or aryl group. So here you can see carbon atom is forming a sigma bond with the oxygen atom, which is shown here. One hybridized orbital of carbon and one hybridized orbital of oxygen is overlapping with each other and forming a sigma bond here, right? Another sigma bond is formed between the hybridized orbital of carbon and this carbon, which is shown by the bond here. Another one one is formed here, which is also a sigma bond. So this is one sigma bond, this is another sigma bond, this is another sigma bonds. So totally 3 sigma bonds are formed. Now what about these 2 orbitals you can see laterally? Yes, these 2 orbitals are the unhybridized orbital. That is one of the carbon atom and unhybridized orbital of oxygen, which is not taking part in hybridization, right? This is one orbital of the carbon and one orbital of the oxygen. Now these will overlap in sideways, okay? Like this they will overlap sideways. That is how pi bond is formed. So what you can say, there will be 3 sigma bonds and 1 pi bond which is formed, right? That is 1, 2, 3 sigma bonds, and the other bond which is shown here is a pi bond. Clear? Okay. So I hope the structure and nature of the carbonyl group is clear for you. Now, the carbon-oxygen double bond is polarized due to the higher electronegativity of oxygen relative to carbon. So, what does that mean? You have other alkyl or aryl groups here. So, if it is aldehyde, you have like this R and H. Okay. So, because of the electronegativity difference between oxygen and carbon, what happens is double bond will be, that is the shared pair of electrons will have more attraction towards oxygen. So, oxygen will get a negative charge and carbon will have a positive charge. So, the bond, that is this carbon-oxygen bond is polar in nature because of the electronegativity difference, right? So, the electrons, particularly the loosely held pi electrons, are pulled strongly towards the oxygen atom to give oxygen a partial negative charge and carbon a partial positive charge. So, the double bonds are present here, right? So, the pi electrons are being attracted towards the oxygen atom, which is more electronegative. Thus, the carbonyl carbon is an electrophilic. It is an electrophile, carbonyl carbon. Okay, carbon is an electrophile. Why? Because it is positively charged. So, it acts as a Lewis acid. It accepts electron. It is ready to accept electron because it is positively charged, right? And carbonyl oxygen will act as a nucleophile. That is Lewis base. It is negatively charged. So, it is ready to accept positive charges. So, it is going to be a Lewis base. That is, it is ready to accept H+. Clear? Now, so we are moving on to the different methods of preparation of aldehydes and ketones. So these methods can be used for the preparation of aldehydes as well as ketones. So the first one is by the oxidation of alcohols. Oxidation means either it is addition of oxygen or removal of hydrogen. So here we are going to remove hydrogen. Okay. So aldehydes and ketones are generally prepared by the oxidation of primary and secondary alcohols. So what you have to remember is, if you are using a primary alcohol, if it is undergoing oxidation, you are going to get an aldehyde. If it is a secondary alcohol which you are using, you are going to get a ketone. Okay, so this you have to remember. So the first one is RCH2OH, which is a primary alcohol. Okay, undergoes oxidation to form aldehyde. So what is happening? Hydrogen is being removed from here. 2 hydrogen, that is H2 is being removed from here, and you are going to get RCHO. That is RCH2OH, right? It undergoes oxidation, that means removal of oxygen. So this 2 hydrogen is being removed. So what will happen? To balance the valency, this is going to be double bond. So what you are going to get? RCH and double bond O. So you get an aldehyde, right? Now considering ketone, so what is going to happen here? Here also hydrogen will be removed. You have RCOR dash. What is RCOR dash? It is ketone itself, right? Clear? So if you are using a primary alcohol, you get an aldehyde. If you are using a secondary alcohol, you get a ketone. Clear? Now the next one is by dehydrogenation of alcohols. Dehydrogenation means what? Removal of hydrogen itself. So in this method, alcohol vapors are passed over heavy metal catalysts like silver or copper. Primary and secondary alcohols gives aldehydes and ketones respectively. So here also primary alcohols will give aldehydes, secondary alcohols will give ketones. So primary alcohol RCH2OH, primary alcohol we have taken in presence of copper at 573 Kelvin, we are going to get aldehyde. Again, hydrogen will be removed from here. Secondary alcohol also you can see here, hydrogen and hydrogen will be removed. H2 will be removed. So what you will have? RCOR dash, that is ketone. Clear? So these two methods are similar itself. Oxidation and dehydrogenation means it is the same, but the conditions are different. Okay, clear? Now the next one is from hydrocarbons. So under hydrocarbons, the first method is by the ozonolysis of alkenes. Okay, alkenes we are going to take. Ozonolysis means ozone we are going to add, O3. Okay, so ozonolysis of alkenes followed by a reaction with zinc dust and water gives aldehydes, ketones, or a mixture of both depending upon the substitution pattern of the alkene. So let us understand how this is happening. So we have taken an alkene here, CH3, CH double bond, CH2, which is propene, to which we are going to do ozonolysis, addition of O3. So how simply you can do this in an easy way is that You can see a double bond here. Right. So we are going to add ozone where the double bond is present. Okay. The ozone will be added to the place where the both carbon atoms are doubly bonded. So one oxygen atom here, another oxygen atom here, and another oxygen atom here. So like a house structure, you are going to add the ozone here. Okay. So when I am adding O3, what will happen to the double bond? Of course, it is going to break. Right. So this bond is going to break and another bond is going to be formed between the 3 oxygen atoms. So that is what is shown here. CH3 will be there itself. CH will be also there. Then you have oxygen. Then you have the other CH2. Then O and O. I hope it is clear. So where the double bond is present there in the house shape formed, you add O3 there. Clear? So of course this bond is going to break. Now how you can remember what is going to happen here is, in this way the bond is going to break. In this way the bond is going to break. So what will happen? See, in this side, what is that you are having? You have the CH3, you have CH and O. What is CH3CHO? It is an aldehyde, right? CH3CHO, that is ethanol, is obtained. Now on this side what you are having? CH2O. CH2O, only this much. This oxygen doesn't count in this, okay? CH2O. What is CH2O? It is HCHO. What is HCHO? It is methanol. So you are getting a mixture of 2 different aldehydes, that is ethanol as well as methanol. So this oxygen is going to combine with zinc and form zinc oxide. Clear? Now let's take another example of 2-methyl propene. Right. So here also double bond is present here. So we are going to add the ozone here. So what is going to happen now? See, of course, this double bond will break. So that structure is shown here. So this intermediate structure is called as ozonide. Okay. So this intermediate structure is called as ozonide. Now what is going to happen? Again, we are going to break the bonds in this format. So what you are having? CH3, CH3 and you have O. That means it is CH3, CO, CH3. This bond is breaking means carbon should have 4 valency, right? So this is going to be CH3, CO, CH3. What is CH3, CO, CH3? It is ketone, right? You are getting ketone as well as CH2O. What is CH2? So O, already we have discussed, it is HCHO. Clear? So this is ozonolysis, which is clear for you. Right. Moving on to the next one, by hydration of alkynes. So to alkynes, that is triply bonded system, we are going to add water. Hydration means addition of water. So addition of water to ethyne in the presence of sulfuric acid and mercuric sulfate gives acetaldehyde. All other alkynes gives ketones in this reaction. The first and the simplest alkyne is ethyne, right? To ethyne, if you are adding water, that means if ethyne is undergoing hydration in presence of sulfuric acid and mercuric sulfate, you are going to get an aldehyde. So apart from ethyne, if you are taking any other higher alkynes, what you are going to get? You will get a ketone. Okay. So ethyne, let's see, addition of water, HOH, right? So H is going to attach in one carbon atom, OH is going to get attached to another carbon atom. So you are going to get CH2 here, right? CH2, and already one CH is there to which the OH will be attached. So it is going to be CHOH. Now what is this? CH2, C double bond OH. So now moving on to the next one, which is a higher alkyne, which is propyne, CH3C triple bond CH. To that we are adding water in presence of sulfuric acid and mercuric sulfate. Again, to this, it is an unsymmetric alkyne. So, according to Markovnikov rule, the addition will happen. That is the negative part. That is in water, which is the negative part. Hydrogen is the positive part. OH is the negative part. Negative part will be attached to the carbon atom having lesser number of hydrogen atoms. We have already studied Markovnikov rule. So, OH will be attached to this carbon atom because it is having lesser number of hydrogen. Hydrogen will be attached to this carbon atom as it is having more number of hydrogen atom. So, you are going to get CH3, COH and double bond CH2 you are going to get. So that is the ketone which is going to be formed. Clear? So I hope that is clear. So moving on to the next one, which is preparation of aldehydes. That is only the preparation of aldehydes. So till now the methods we have discussed were the preparation of aldehydes as well as ketones. Here it is just the preparation of aldehydes. So the first one is from nitriles, which is called as Stephen reaction. So reduction of nitriles. What is nitrile? Nitrile means RC triple bond N is called as nitrile. Okay. When reduction of nitriles, reduction reduction. That means we are going to add hydrogen. Reduction means H2 is going to be added. Okay, with acidified stannous chloride, SnCl2. Acidified means in presence of some acid. At room temperature, it gives aldehydes. In the first step, imine hydrochloride is obtained, which on hydrolysis with boiled water gives aldehyde. This specific type of reduction of nitrile is called as Stephan reduction. So this is a named reaction. It is important. So this is your nitrile, RC triple bond, and R can be alkyl group, any alkyl group. So what happens? To this we are going to add hydrogen, means H2 we are going to add. One hydrogen will be added here. One hydrogen will be added here. So what you are going to get? RCH double bond NH. So this is your imine which is formed. Okay, on either side hydrogen will be added. So this triple bond will become a double bond. Now once imine, which is the intermediate state. So once imine is formed, we are going to boil it, right, in presence of water. So what you are going to get? You are going to get the corresponding aldehyde. Okay, we are going to get the aldehyde. Clear? Now, moving on to the next one, ethane nitrile, that is CH3, C triple bond, and again addition of hydrogen on both sides we are going to get it, CH3, CH double bond, NH, okay, and then again addition of water, that is hydrolysis, and boiling it will give you the corresponding aldehyde. So, CH3, CHO you are going to get, and this part will be broken and NH4Cl will be formed. So, this will be the corresponding aldehyde which will be formed, that is CH3, CHO. Clear? So, important parts to remember is what is the reactant and what is the product that you are going to get. In this case, you are going to get aldehyde, and which is the reagent that you are using for Stephan reaction, that is stannous chloride and HCl. The next one is alternatively nitriles are selectively reduced by diisobutyl aluminium hydride, which is called as dibal H. Diisobutyl aluminium hydride is called as dibal H. To imines followed by hydrolysis to aldehyde. The same reaction is going to take place, but we can use another reagent that is called as dibal H. So if RCN we are going to take, RCHO you are going to get. CN will become CHO. Clear? Okay. So the first step will be again the formation of imine, and then after hydrolysis you will get the aldehyde. So CH3, CH double bond, CH, CH2, CH2, CN you are having. Nitrile is present here. In the presence of dibal H, first step, imine will be formed. Second step, hydrolysis, your corresponding aldehyde will be formed. Again, this much part will remain the same. Nothing will happen to the double bond also. CN will change to CHO. Aldehyde you are going to get. The next one is from esters. Esters are also reduced to aldehyde with dibal H. Okay. So, nitriles can be also reduced to aldehydes, as well as esters can be also reduced to aldehydes using dibal H. So, you can see CH3, CH2, 9 times CO, OC2H5. So, the COO, this is your ester, right? In presence of dibal H, what you are going to get? This part will remain as it is. This is going to break and you will get a CHO here, right? So, this will be removed as alcohol. So, this part will be COHO. Clear? So, that will be your aldehyde which is formed using dibal H. Next one is from acetyl chloride, or else it is called as Rosenmann's reduction. So, this is also named reaction. This is very important. Aldehydes are prepared from acid chlorides by reaction with H2 in the presence of palladium catalyst supported on barium sulfate. This reaction is called as Rosenmann's reduction. So, acid chloride or acetyl chloride we are taking, which is obtained from acid. That is why we call it as acid chloride. RCOOH is the acid. Instead of OH, Cl will be there. To which we are going to add hydrogen in presence of palladium and barium sulfate. Okay. So, the reagent used in Rosenmann reduction is also important. Okay. So, all of this, what is the reagent that we are using, what is the reactant, what is the product we are getting, all of that are important. So, what is going to happen? Yes, hydrogen, one hydrogen, H2 we are adding, right? One hydrogen will be added here, another hydrogen will be taken out with the HCl. Clear? So, you are going to get HCl and aldehyde. Clear? So, let's take CH3CuCl. Okay, what are we going to do? Addition of hydrogen in presence of palladium and barium sulfate. So, you are going to get CH3CO and this H will be added here. So, you get CH3CHO aldehyde. Which aldehyde it is? Acetaldehyde and HCl. Right? The next one is preparation of benzaldehyde. So, we are going to discuss aryl aldehyde here. So, Itard's reaction, this is called as Itard reaction. Again, it is important. Chromyl chloride, CrO2Cl2. So, this is the initial thing we are going to use. So, chromyl chloride oxidizes methyl group of toluene to a chromium complex which on hydrolysis gives benzaldehyde. So this is called as Itard's reaction. So this is methyl benzene, which is called as toluene. We already know that, to which chromyl chloride is going to react, CrO2 Cl2. Okay, what are we going to obtain? We are going to obtain a chromium complex. Okay, so this is going to get added up here instead of a hydrogen atom. So you are going to get a chromium complex here, which on hydrolysis, you already have a CH here, right? That means it was CH3 here, one hydrogen atom was being removed, and you are going to get the chromyl chloride part here. So now what happens? It undergoes hydrolysis and forms aldehyde. That means oxygen will be added here. That is this OCrOHCl2 means CrO2Cl2 itself, your chromyl chloride itself. Clear? So this is Itard's reaction. So the next method is using chromic oxide, CrO3. So that was chromyl chloride, this is chromic oxide. So toluene or substituted toluene is converted to benzylidene diacetate on treating with chromic acid in acetic anhydride. The benzylidene diacetate can be hydrolyzed to corresponding benzaldehyde with aqueous acid. So this is again toluene which we are taking. So to that we are adding the acetic anhydride. Okay, to that we are going to add the acetic anhydride. Now what happens? What is acetic anhydride? CH3CO, CH3CO. So this is acetic anhydride in presence of chromic oxide. So again you are going to get a chromium complex, and then hydrolysis you are going to get the benzaldehyde. The next one is by Gattermann-Koch reaction. Again it is very, very important. Benzene or its derivative is treated with carbon monoxide and hydrogen chloride in the presence of anhydrous aluminum chloride with traces of cuprous chloride. Benzaldehyde or substituted benzaldehyde is formed. This reaction is called as Gattermann-Koch reaction. So benzene or derivatives of benzene also you can take. That means there can be other substituents also. So it is going to react with carbon monoxide and HCl in presence of anhydrous aluminum chloride and a little bit of copper chloride and a little bit of cuprous chloride. So what is going to happen? Here the aldehyde group is going to be substituted. So you are going to get a benzaldehyde there. Clear? So here what you have to remember, what is the reagent that we are going to use. So until this what and all reactions that we have discussed, most of them are the name reactions. So of course it is really important for your examination point of view as well. So what you have to remember is what is the initial reagent that we are using, right? As well as what is the reagent that we are using. Okay, for each reaction it is different. It is very, very important to remember that. They can directly ask you also which is the reagent that is being used for example, Stephen's reduction, for Rosenmann's reduction. So that also you have to remember. Clear? So in the next session we are going to study in detail about the preparation of ketones separately. So I hope the concepts that I've covered in the session is clear for you. So that's all for today. Thank you.